Alright, number 17. How many 4 times 4 arrays whose entries are zeros and ones are there such that the row sum are 1, 2, 3, and 4 in some order, and the column sums are also 1, 2, 3, and 4 in some order? Well, now when we look at this array right here, we know that this row sum, which are specifically these, well, let me just change the color to be blue. These are actually 3, 2, 4, and 1, which are obviously permutation of 1, 2, 3, 4. Now, what about columns? We also have this 2, 4, 3, and 1, which is also a combination of 1, 2, 3, and 4. Now, what if we just vary the row sum and the column sum? Now we have a 1, 2, 3, 4, 1, 2, and 3, 4. Now we actually have, we can just make a 1 here. Then we make, well, actually, we must have 1 to be in this case. We know that all of these must be 1. So, therefore, from here we have all of these to be 0. Now, 2, 3, and 2, 3. So we can just, seems like, choose these to be the subsequent numbers. And we can see that there's actually only one way, because we must fill those of 3, right? Now what about we try another one? Now let's say if we have something like 1, 3, 4, 2, and for the row sum we have 2, 4, 1, 3. Now what do we do? So from here we can first fill those of 4, the row and the column of 4, because we know that in those row or column all 4 must be 1. And same for 1, since we already got those of 4, then we can actually fill in 0 for that respective column and that respective row. Now we can see that because this row requires numbers and all of them must be 1, so these are just all 1s, and same as this 1, 0. Okay. So from this process that we have done, it seems like that when we just have a stationary or a controlled row sum or column sum, or we have these controlled ones, then it seems like all of the numbers are actually being determined. For example, we must fill all of the numbers over here to be 1, same as this, and we also have all of, then we got a 1, then we actually have to fill all of the numbers on the row or column of 1 to be 0. So same as this, same as this. Now from here, we can just do the 3 ones because we have a 0 on those. So therefore, we must fill 1 on all of them. So let me just denote a different color. Now at the end, we can just determine 2 from what we have. Okay. So from here, you might not determine a pattern yet. However, this basically says that there's actually a unique kind of distribution of 0 to 1 for each of the stationary row sum and column sum from the example that we have determined here. So basically, the problem just transforms to the problem that what is the number what is the number of permutation of 1, 2, 3, and 4 are there for both row sum and column sum. So basically, well, it might be like kind of ambiguous for this wording. However, the new problem is basically saying how many ways are there to arrange 1, 2, 3, and 4 twice, basically, right? And we see that basically these two permutations are independent of each other. So basically, this means that we have 4 here, then those will like not impact any of the numbers put it in this row sum. So simply the answer would just be 4 factorial, which this 4 factorial is the number of ways to arrange 1, 2, 3, and 4 for the row sum, and multiply by 4 factorial to arrange the column sum. Now this one simply just becomes 24 times 24, which is equal to 576. And that gives us our answer choice, D. Now, go on to the next one. Problem 18. Each square in a 5 times 6 grid is either filled or empty, and has up to 8 adjacent neighboring squares, where neighboring squares share either a side or a corner. The grid is transformed by the following rules. Any filled square with 2 or 3 filled neighbors remains filled. Any empty squares with exactly 3 filled neighbors becomes a filled square. All other squares remain empty or become empty. This will just be a sample transformation. So let's look at how did this square transform to the other square. So basically, neighbor square there are actually 8 neighbor square. What does that mean? Basically, for this square, we actually have 1, 2, 3, 4, 5, 6, 7, and 8 neighbor squares. So basically, all of these squares are neighbor to this one. So now let's look at this square. So this square would obviously not be filled after the transformation. However, this one would be filled because we have 1, 2, and 3 neighbors. Now after this square is filled, then we know that this square must also be filled. And if this square just remains filled, it just not become empty. And from here, we know that this square would also be filled. Suppose the 5 times 5 grid has a border of empty squares surrounding a 3 times 3 subgrid. How many initial configurations will lead to a transformed grid consisting of a single filled square in the center of their single transformation? This problem seems to be a bit tricky. Well, you might just be scared off based on the giant, enormous reading that is contained inside this problem. However, let's try to break it down one by one. So you can see that if initially we have some transformation right here, well, some configuration, and at the end we only have 1, then it might just be, well, this case, right? Because we only have 3 squares. However, and also, would it just be any 3 squares inside this? Well, not necessarily, however, it might just be the case. So we can just choose any 3 squares on the... Yeah, we'll just choose any 3 squares inside this surrounding. So, well, however, we cannot have something like this, because obviously we cannot have this, because this one will be colored and this one will also be colored. And after this, see that this one will just remain to be black. So this idea would just not work, simply. Now let's look at how can we tackle the problem in another way. So well, obviously the square, for example, like this, we'll shade this one and this one will still be black. Well, what about when we have something like this? Then we know that this one will be shaded and this one will also be shaded. Where neighboring squares share either a side or a corner, the grid is transformed by the following rules. First, any filled square with 2 or 3 filled neighbors remains filled. Any empty squares with exactly 3 filled neighbors becomes a filled square. And any all other squares remains empty or become empty. A sample transformation is shown in the figure below. So just a quick demonstration. In this case, we have that this one would actually, any filled square with 2 or 3 filled neighbors remains filled. So we know that this one would actually just vanish. And any empty square with exactly 3 filled neighbors becomes a filled square. So we actually know that this one would actually become filled. And from that this one would just get away naturally. And only 2 or 3 filled neighbors become filled. So this basically means that actually this one would actually become a filled square. So it's actually demonstrated in this right hand side. So now let's go on to the actual problem. Suppose a 5x5 grid has a border of empty squares surrounding a 3x3 subgrid. How many initial configurations will lead to a transformed grid consists of a single filled square in the center after a single transformation? So this just basically means that after a single transformation, no other square except the center square is filled. So for this problem, our approach would actually just be casework. So let's think of 2 cases. So first, if we have the center square to be filled, then what are the cases that would actually make any other square that is urgently shaded to vanish? Well, first, obviously this cannot go alone, so we probably would have either 2 or 3 surrounding squares. Now, what if we just have something like these 3? What if we have 3 surrounding squares? Then, well, this one would actually be shaded, which is not what we wanted. And it's actually possible to prove that any possible combinations of 3 shaded squares that are around would actually create another shaded square that's additional to the middle one. So we don't want 3 extra shaded squares. Now what about only 2? 2, if we have let's say these two, then this one will actually be also shaded. And what do we have these two? So basically, if we have any that are actually adjacent or something like this, then some other square would actually be shaded. So therefore, we cannot create a 3 shaded square border with 2 additional ones. So the only case would just be when they're actually lying on the diagonal. And going back to the problem, it's actually saying that rotations and reflections of the same configuration are considered different. So this means that we actually have, instead of 1, there are actually 2 cases. We can also have it lying on the other diagonal. So basically this would actually give us 2 cases. Right, let's go to the next case. Case number 2 is what? Case number 2 is basically means that the middle square is actually not shaded. So how would this actually be carried out? Let's still draw the 3 times 3 square to see what will happen. So we have the square drawn. Now we know that the middle square cannot be shaded. So therefore, we must have either we must strictly have 3 squares that are on the border, or out of these, there must be 3 of them that are shaded, because recalling the rule that any empty square with exactly 3 filled neighbors become a filled square. So therefore, we know that there must be 3 surroundings. So let's just do some casework. Or actually, we're going to just try to exclude which of them are not going to work. Also, first, we know that we have something like this, then the middle one would actually be shaded. And we know that, well, in fact, none of these would vanish because they all have 2 or 3 shaded squares that are on their border. So this essentially just means that these 2 would also appear naturally, and that is not what we want, because we actually want only this one to appear. So we know that this case would actually not work. Now let's go on to the next case. The next case is when we have, or what if we have something like this? Then for this case, we would have the middle square to be shaded. Well, this one actually we can just shade the middle square, so we know that the middle square must be shaded. So basically we just consider how many ways are there to add 3 such that no other squares would be created, or the old square will also not be created. So basically these would actually all vanish because they only have 1 neighbors. So therefore this one would actually work. Now let's go on to the next one. Now, what about something like this? Why should we just know that we cannot have 2 of them occupied at the same time? So, therefore, this one would also, in fact, just work because all of these would actually be deleted. So this also works. And let's go on to the next one. Now we can actually have only one neighbors, but the other one must actually just like fly away. But we still cannot have something like this, since this will actually create some more. So therefore the case would just be if it lies over here, then this one would also work. And let's think of any more cases. Well, this is actually the last one, would just be the same idea, which is just we have one like over here, one over here, and one at the corner, so that we know these would vanish. So we can make that these individual squares vanish, then we know that this must work. So therefore these would also work. And there aren't any more cases, because other than that we will actually create a border so that these red squares will actually not vanish. Now let's just find the number of ways for each of the configuration to exist by considering the rotations and reflections. So for this one, we know that we can actually have this configuration. Excuse me, let me just make this to be a little bit thicker. We can have this, or we can also have this, and we can also have on the other way around this. So there's actually 4 ways. And what about this case? Well, this case, we just consider the position of this square. So this square, obviously, we can have all of the following ones. We can have over here, over here, over here, over here. So another 4 cases. Now let's go into this one. Well, for this one, we'll actually just consider the number of ways for these to be settled. So for this one, for each of these square, we can consider the number of cases of this square. So let's think about for this square. How many ways are there? Okay. Well, actually, in fact, it would just be simpler to do this. So we know that for these 2 squares, the square can actually be over here, or it can also be over here. Well, actually, excuse me. For these 2, we know that it's actually binded to this point. But actually, there's actually 8 of such adjacent 2 on the bottom. For example, like this, 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 and this. There's actually 8, and for each one we know that it's binded to exactly 1. So therefore, this will actually create, in fact, 8 choices. And for this one, obviously, we have 1 configuration for each of these squares in the corner. So therefore, there's actually 4. So if we just sum up all of the numbers, we get 2 plus 4 plus 4 plus 4 plus 8, which is equal to 22. And that gives us an answer choice C. Now let's go on to problem 19. Problem 19, in triangle ABC, medians AD and BE intersects at G, and triangle AG is equilateral. The cosine value of C can be written as m times square root of p over n, where m and n are relatively prime positive integers and p is a positive integer, not divisible by the square of any prime. What is the value of m plus n plus p? So for this one, we actually need some more space. So let's just draw an accurate diagram. We have this triangle right here, and it's saying the medians AD and BE. Just mark this A, B, and C. Now the medians AD and BE, which this would be D and this would be E respectively. intersects at G. And it's saying that triangle AGE is equilateral, so basically meaning this triangle is equilateral. So what it's trying to find is trying to find the cosine value of this angle. So we want to find cosine. So for this problem, we first want to consider the relationship between medians. So basically, if we have medians, then we know that because E is the midpoint of AC, then AE is actually equal to EC, and we also know that BD is equal to DE analogously, because D is also the midpoint of BC. So, and we also know that in fact this triangle AGE is equilateral. So let this just be M. We'll just do a little bit of length chasing, M and M. Then this one, we actually know that for a median, the intersection, which is actually in fact called the centroid, then the ratio of these would just be 2 to 1. So this essentially just means that this piece of length is equal to M over 2. And this one is in fact equal to 2M. Okay. And we know that this length would actually also be equal to M. So now I want to find this alpha, this angle. So how are we going to work that out? So basically, what if we just look at this triangle right over here? Well, actually, we can also first look at the right triangle here, which would also work. So we know that this angle is actually 60 degrees. Because of vertical angles, then these two angles are actually the same. So we know that BD, we would just break out some law of cosines. The square root of 2m squared plus m over 2 squared minus 2 times minus 2 times 2m times m over 2 times the cosine value, which is just 1/2, equal to the square root of 4m squared plus m squared over 4 minus, when these two just cancel out, these two also cancel out, so it's m squared. So this one is actually just 13m squared over 4. It's root 13 over 2 times m. So we know that this part is root 13 over 2m. So therefore the entire part should just be c. That is actually just equal to root 13m. Alright. Now we can just break out the law of cosines for this triangle right here. Since we know the length of this, and this, so we can just find the cosine value easily. I recall that I want to recall that BE squared is actually equal to BC squared plus C squared minus 2 times BC times CE times cosine of C. So we can just isolate this out with BC bc squared plus ce squared minus b squared. That is equal to 2 times bc times ce times cosine of c. And we'll just isolate by divide both sides with 2 times bc times ce. Then we actually get that bc squared plus ce squared plus minus Alright. Now we have this, we just plug in values. So BC is actually root 13. CE is actually equal to 1, and BE is actually equal to 3. Well, this is just because we simply just scale it down by m, because the cosine value wouldn't change for similar triangles. So we got 13 plus CE is just 1 square minus 2 square. No, minus 3 square, excuse me. Over 2 times root 13 times 1. Well, this one just simply becomes 5 over 2 root 13, and don't forget to rationalize, because the answer is n root n over p, which definitely is after rationalization. So this just becomes 5 times the under root of 13 over 26. And this matches our answer choice form, n root p over n. So the answer is simply just 5 plus 26 plus 13. That is just equal to 44 as our answer.